Welcome to the HeatWise tutorial video, where I'll be showing you how to create a project and go through your heating and cooling load calculations from start to finish. So starting from the home page, what you would do is go log in. This will take you to the application page. From here you can log in or create an account. You can also sign in through Microsoft if you prefer. So since I already have credentials here, I will just do a simple login. Once you log in, it will take you to your main project dashboard where you can see all of the projects you've created, as well as the projects that have been shared with you. So for this example here, you can see I've created one project so far. It will also tell you the number of people that you've shared your project with. They will show up under this shared with column. There's also a locked column. This will tell you if anybody is currently editing the project that you've shared with them. As the owner of a project, you can always choose to kick someone out if they are currently editing it to give you full control over the project. But this will tell you if somebody is currently using it. Any projects that are shared with you will show up in the second list down here. So to create a new project, what you do is go click Create Project at the top here. You then select whether it is a commercial building or a house. So we'll go with commercial building for this example, and then you would give it a name. Hit create. This will take you to the project guide page. So this is kind of your home page while creating your project. So we'll go over a few preliminary items before we get started. If you look at the top right corner over here, you'll see a letter, and that will just be your basic account options, so you can sign out or access your account settings from here. You can also use the send feedback button if you'd like to request new features, or you've encountered any problems or have some feedback to send. You can send a message to the development team and they will address it. You can also use the Get Help button if you need help with any particular part, or you have been you've been stuck at a certain item that you're not sure about or don't know how to proceed. You can request help from the development team. You hit send, and they will reach out to you shortly. You'll also see in the top left corner this All Projects button. This is how you return to your main dashboard, where you can view all the projects that you've created that we just looked at before. So clicking back into the one that we were just creating. This left-hand menu here will show you all of the tabs and the different pages that you can use while editing your project. So throughout this tutorial, we will go through each one of these. You'll also see your settings at the bottom here. So this is where you access your basic account, basic settings for the project. So you can rename your project here, export your project, or you can actually delete the project, which requires you to go through a confirmation to make sure you don't actually or accidentally delete your project. You'll also see your project sharing here. So to share a project, you would simply click Add User and enter the user's email address. This email address that you enter, it'll send an automatic email to that person notifying them that a project has been shared with them. So even if the person that you've sent it to hasn't yet created a HeatWise account, the email will still be sent to them, and once they do create an account, then it will show up in their shared project list right here. And the last item to show you before we get started is the Quick Help button in the top right corner. At any time you can click this and it will expand a window for you, which will give you some basic instructions and descriptions about the inputs, or the relevance of the inputs in terms of how they will affect the calculations. So you can always refer to this. It will be different for every tab that you're on as you go through your project. At any point you can also hit the X button to get rid of it if you don't want to see it. So once we've, now that we're done these preliminaries, we can move on to the actual preliminaries or first steps of the project. So from the project guide, you'll see that step 1 is setting a location, and we've got this arrow telling us that the location is what we're supposed to be doing next. So you can see it's set to a default value, but you can change this by selecting your country. So for this example, we'll go with the United States, and then you select your state and then your city. At any point, you can always just change that location again to whatever you like. If you don't see your country or don't see a particular location that you would like, you would click this "Don't see your location," and you can type the specific place that you'd like to have included in this list, and it will be sent to the development team, and somebody will reach out to you regarding that request. So once your location is set, you can view the weather data by clicking Show Data. So you've got your high-level parameters. You've got your heating design temperatures, cooling design temperatures for 0.4%, 2%, 5%, and 10%, as well as your daily temperature ranges and solar irradiance values. All of the values within this pop-up can be overridden. So for example, if I wanted to change my peak heating temperature, I would just click Override, and I can enter whatever value I'd like. If you'd like to return to that at any point, you just click Show Data again. And if you'd like to go back to your default value for your location, you would just hit the X next to the Override button, and it will return to the starting point. There's also an advanced drop-down section here. Again, it's described on the Quick Help menu, so if you're unsure of any of this, you can always refer to that. This is for your ground reflectance values. It's separated by the different faces of your building. So north would apply to anything north, like the north, northeast, northwest, east, northeast, east, southeast, and so on. It's also split into summer and winter values. So you can select a snow-covered ground type for winter if that's expected in your location. And you can change the ground type for the different faces of your building. So, for example, green or dry grassland, desert if you had that. And the value shown here is the albedo value, so that is the solar reflectance off of the ground at that point. So once we're done with the location, we can return to our guide and click Mark Done and move on to the second step. So the next step in our project is to create our spaces. So we'll go to the Spaces tab on the left here. You can see so far we have no spaces, so we'll go Create. And first thing you want to do is give your space a name. So for this example, I'll just call it Office 1. Now, the Spaces tab is where you're going to spend most of your time while creating a project. So we'll go through kind of a high-level overview first and digress into some of these tabs on the left here under Components as we do so, because those are necessary before completing the space. So you can see these spaces inputs are separated into 3 categories. We have our general inputs, our envelope, and our internals. So let's start with general. So we've got our floor area, which is something you would get from your architectural plans. For this example, I'll go 150. Average ceiling height will also be from your architectural plans, and we'll go 10 feet for now. This more info section here is a little bit less obvious. This is to do with the radiant time series calculations, which are a little bit complicated. As far as you need to know when creating a space is you can just use this construction weights reference to help estimate your construction weight. You'll see that you've got light, medium, and heavy, and descriptions of the building envelope and furniture and so on. So for this example, I won't dive into the details there. I'll just assume it's a light construction. It's an exterior zone for this example. Percent glass, you just have to make an estimate between these 3 values. So we'll go 50% for this, and we'll say it does not have a carpet. So some of these you may not know and you may have to make an estimate. Um, but what these inputs are doing are generating these vectors down here, which has to do with the time delay of how the radiant heat gains are experienced in the space. It gets a little bit complicated, so I won't go into the details of how it all works here, but what you need to know for now is that you can watch how these vectors change as you change your inputs. So if we go heavy, you can see the numbers changed, the shape of it changed, and this can be easily seen as you modify these inputs. For a little extra description, you can always click these bubbles where you have an eye. It will give you a quick description of the inputs, and you can also refer to your quick help, which will help give some advice on how to provide these inputs. So moving on from general, we'll go to ventilation. For ventilation, you have two different options of how to enter the inputs. You can either go manually or entering automatically. So if you know the exact values you want to include, either a CFM value or if you want to go CFM per person, square foot, or an air changes per hour, you can do that. So if you knew the CFM per person and the CFM per square foot, you could enter both of these values and it will generate a total ventilation based on the inputs you've given. So for example, if we went 0.06 CFM per square foot, based on the square footage we gave in our general inputs, it generates a total ventilation. So for example, if we change this to 200, you would see this calculation automatically updated. We haven't entered our occupancy yet, but once you do, you would see this value change as well as we change our occupancy. So for now, I will return back to our original values. The other option being entering automatically. You can select a space type and it will automatically populate the CFM per person and per square foot values. If you want to change it, it defaults to office space, so if you like to change it to anything, you can click change. And these occupancy categories come from the ASHRAE 62.1 standard and auto-populates from those tables. So for example, we could go retail, sales, and you'd see 0.12 per square foot and 7.5 per person. Since this was an office, I will return back to that office space input. And you can also click the more info drop down to show you the breakdown of where these calculations are coming from. So the next part of the ventilation inputs would be the effectiveness, and this is also a value from the ASHRAE 62.1 standard. And you can see that here in our quick help. A brief description of effectiveness and what to do if you don't know your values. There's a ventilation effectiveness reference table. So if we click that, it will give a description of different types of air distribution, so air supply and return based on temperature. So if you don't know those values, it's usually best to just leave it as 1. But if you do know the values, you can enter them from that effectiveness reference table. So I will change these values now to what I expect. So moving on to the infiltration inputs, similar concept where you can select how the infiltration input will be taken in and processed. So you can go by square foot of exposed area per foot of crack length. So the cracks would be, for example, the window perimeters and door perimeters, or you can go with an air change per hour. So for this example, I will go with a CFM per square foot of exposed area. I will not be adding any for summer, so I'll just enter what I expect for this type of space. You can also go with adding your infiltration only during occupied hours if your fan systems are off when the building is unoccupied. But for this one, I will leave it as all hours. And you can, again, click your more info drop down to see how your calculations are showing up at the moment. So because this is at CFM per square foot of exposed area, and we have not added any exposed area, being walls and roofs. It's currently at 0, but as we go and update those values, you'll see that this value will change. So now that we've finished our general inputs, we can move on to the envelope inputs. So we start with the walls. So you can see here we have no walls yet, so you just have to click Add Wall, and we've got our first wall here. So you can see that under the Type column, we've got no value. Right now it says Select, and if we do that, we've got no walls to select from, and that's because we have not yet created a wall type. So what we'll do here is go Create Wall, and this brings us to our wall creation pop-up. So first thing we'll do is give our wall a name, and for this example I will just name it Brick Wall. You then have to go through the process of entering all the necessary inputs. So first thing we do is select the type of wall. This doesn't necessarily have to be exactly matching your wall type. The more accurate you can get, the better. What this really does is affect the CTS vector down here, which I'll describe in a minute. The next part, and the most important part, is the thermal resistance of the wall. So you can enter your thermal resistance manually, or you can build the wall from wall materials. So I'll show both methods. So if we were to build a wall, what we would do is add layers, and you can see there are 2 default layers already added, and that's the resistance between the air and the surface of the wall on both the outside and the inside. So we can add a few layers, and you will have 2 inputs. You've got your wall material category and then the specific wall material. So for this one, we will just go with a few options here. I'll try brick fired clay low density, and you can see we'll also be required to enter a thickness input. All of this information should come from the architectural plans. If it's an existing building, sometimes it's very hard to estimate, and that's why you just have to do the best you can with what you've got. So for this one, I will just give an estimated 2.5. You may have a building board type, so we'll just do a few little example inputs, and almost certainly you will have some kind of insulation. So I will just go with glass fiber batt insulation, maybe 3.5 inches, and you will get an R value output. One of the advantages of building your wall is that it also provides you with an exterior wall weight if you've got all of these accurately inputted, because if you decide to manually enter, you will have to manually enter your wall weight as well, and that will also impact this CTS vector. Now to do that, you can use your recommended wall weights reference table. So for example, I selected brick wall, and so for a brick wall, typically you'll be in this kind of range. A heavy one might be at 183 pounds per square foot. Light would be around 43, close to 44. I had selected light construction weight in my general inputs, and this is a brick wall, so I'm going to go with on the lighter range. So I will just enter 44. And let's say from our architectural plans, I know that it's an R value of 25, then that's what I would enter. If you'd like to go back to your build wall and just try to be as accurate as possible, you can do that. And you can see that when we switched from manual back to build wall, all of our inputs remained. But for this example, I will just say it the manual input. So the next one on this list is the solar absorptance. Again, you can enter manually, or you can select by material. Selecting by material allows you to select any from this list here, and you can see that each option will have a solar absorptance value in parentheses. So this one will just go with red brick. And our output, which is based on the wall type and the thermal resistance, or sorry, the wall type and the exterior wall weight produces this CTS vector. And this is showing how the wall absorbs and releases heat over time. So the heavier the wall, the more it will absorb material. So for example, if I were to increase this to 180 pounds per square foot, so a very, very heavy wall, we'll see that this plot here becomes much more spread out, so it's more slowly absorbing heat and more slowly releasing the heat. If we went with a very light wall, what we would see is something more stacked at the front end, where it's absorbing heat pretty quickly and then releasing it quickly as well. It's very difficult to get these inputs perfect, but an educated guess is better than no guess at all. So what we'll do is keep it like that, and then we can hit select item. So the wall we've selected for this wall type is now that brick wall that we just created. Now at any point you can view your walls by going to your walls tab on the components, under your components list here, and you can see that the brick wall that we just created now shows up in this list. So now let's say I wanted to create a new wall, and we'll call this one a stucco wall. This is a different wall type on our building. We can just modify our inputs a little bit. So I'll just do a few quick little example inputs using my recommended wall weights. We'll just put 8. You can see our CTS vector is quite different than the last one. And I will pick a different absorption value. Going back to our list, you'll see that we now have 2 wall options. So if we return to our spaces that we were creating this office 1 space, if we decided to change this wall, or at any point if the architect changed the wall type on the plans, we can click the wall type, and what we will have are the 2 options from that walls tab on the left side. So as you add wall types, this list will get bigger and bigger, and you can select whichever one is the appropriate one for this space. You can also edit these wall types from this pop-up within your space editing tab. If any edits are made to the wall type and the wall is used in multiple instances in a particular space or in many different spaces, it will be updated in every instance simultaneously. So if I went to my walls and I wanted to change the R value, let's say it went from 25 to 28, then when I run my loads, since a brick wall was used there and a brick wall is what I just changed, that R value will be updated for when those calculations are performed. So continuing on with this wall input, we have to give the area of the wall. So I'm just going to say it's about 100 square feet. That's about a 10 foot by 10 foot wall. And then select the direction that it's facing. So let's say this one is an east wall. And we now have options to add windows and doors. So by clicking this edit button, it will drop down more inputs. So the first one worth noting is this ceiling plenum input, and this one is a little bit more confusing and might not be super obvious. So if we just go down to our quick help, it describes what this exactly is and shows a diagram. And the purpose here is that if you have a full height wall like this, you want to make sure that you're getting the heat transfer for that entire wall. So in this example, let's say it was a 10 foot by 10 foot wall. We have 10 feet of height and 10 feet of width. But if we had a dropped ceiling that was about 2 feet, so our interior height was only 8 feet, then we'd want to make sure that 2 or 20% of that of the wall load goes straight into the ceiling plenum. And the reason that that's important is because it's not really entering the space then. If that is a return air pathway, then the air will be brought through and the cooling load will be experienced on the return air side rather than on the space side. So in this example, I will keep it as yes, and I will put 10% just as an example here. So that means 10% of the wall load will directly enter the ceiling plenum, and it means that the load, like I said, it will still be experienced, just not in the same way, and it will make some slight adjustments to the calculations. So we can now add some windows and doors. So for windows, you can see this is very similar to what we had when entering our walls. We have to select a value, and we currently have no windows created. So what we would do is create a window. These should come from your architectural plans as well. We will call this one, maybe this is a square window. So you give it a name. We will say this is a 5-foot by 5-foot window. You can select if it's a fixed, operable garden window or curtain wall. And you can select if it has a bug screen. Now you can see there's no option other than none here. And that's because a fixed window would never have a bug screen. But if you went operable, you could select if the bug screen was on the inside or the outside. So for this example, we'll keep it fixed. Very similar to creating the walls, you have your manual option for inputs, or you can build the window. Building the window can be a little bit complicated. You can see that you've got the number of panes, the frame type, the frame width, glazing. Some of these inputs are dependent on others. So for example, if I went 2-pane aluminum with thermal break, our glazing options, we now can add a low emissivity coating. We can apply it to different surfaces. We can add a tint to the window here, although it may be dependent on which surface it's been applied to. So a green, for example. Pane thickness, you have 2 options, and then you've got options for your gap type if your number of panes is greater than 1. And you can see that as you change these inputs, your output SHGC and your U value will change as well. These values come from just empirical data based on these inputs here. What's more common is that the architects will provide you with the specific U value, and so it might be easier to just hit manual, for example 0.3. The more complicated one is the SHGC. This is the solar heat gain coefficient. This one is not known as often. For this example, I'll just go 0.7. This is an item that we will not be diving too far into in this video. There will be a more detailed video on the solar heat gain coefficient and details about the window. So if you are interested in that, you'll have to see that other video. So for now, we'll just kind of make some assumptions here and move on. So we'll select that window, and similar with how we edited the walls, if you go to your Windows tab on the left, you'll see the window we just created. And if you wanted to create a new window, you would just hit create. You can see the quick help provides some guidance on solar heat gain coefficient and U values. Going back to our space, if we wanted to select a different window, we would just go back to the list and we can select any window that has been created in that Windows tab. Interior shadings can be added to windows. So interior shadings are like blinds and shades, roller shades, things like that. It's recommended that you don't add this unless you can be confident that the shades will be used during your or during peak load times. For example, shades that are on automatic timers. For this example, I will not be entering that detail because it is a little bit advanced, and that will be discussed in the more advanced subject matter video on windows and shading. For now, what you need to know is that you can add interior shadings. They can be edited from your interior shading menu, or your tab on the left-hand menu there. You can add a schedule to it if you know that it will be closed during some parts of the day, halfway closed, a quarter closed, and so on. And you can add external shadings as well, and that's things like overhangs. So for example, if you had a balcony and there was a balcony above, you know that that balcony will be shading the window for large parts of the day, especially when the sun is up high. We won't do that in this example here. We'll just continue to move on. But the other item here is that you can add a quantity as well. To any wall, you can also add a door. It's very similar to the windows, and in order to keep this moving, I will not dive into the doors right now, but it's a very similar process to the windows, and if the door has glass on it, then you can also add internal shadings and external shadings to your door as well, and those shading devices will affect the glass portions of your door. So for now, we will keep it as one wall and then move on to the roofs section. You can add multiple roofs. The reason for that being that if you have a sloped roof, you may have part of it sloped one direction, part of it sloped another direction. Adding a roof is very, very similar to adding a wall. It's virtually identical, except for the roof selection comes from the Roofs tab on your left-hand menu rather than the Walls tab. You have the option of adding a slope. Once you add a slope as a percentage, you will be offered the option to show the direction, so you can have an east, southeast, whatever. How to calculate that slope is also shown in your quick help. If we go down to the roof section, you'll see what exactly is meant by that. It's not an angle, it's a percentage, so just keep that in mind. And instead of adding windows and doors, you have the option to add skylights. Skylights coming from the Skylights tab, and creating a skylight is virtually identical to creating a window. Because of how similar it is, I won't dive into this now. We'll actually not add a roof to this example, but creating one and the whole process is basically identical to creating a wall. The next part of your building envelope portion is adding a floor. You can also add multiple floors. It's an uncommon thing, but in case you do have that situation, that is an option. So what we'll do here is show different types of floors. Different floor types have very different input options. So if you look here on the floor type drop down, you've got a slab on grade, a slab below grade, which is the basement, floor above crawl space or unconditioned space, the floor above a conditioned space, or a floor raised off ground. So we'll just go through a few of these quickly, the more complicated ones. So for a slab on grade, you would give the area first. So we'll just say this one was entirely on grade. You give an estimate on the outer wall construction, and you'll see here that these options are very different than options you're given when creating a wall, and that is just because the data does not really require as much refining in terms of just trying to estimate the heat losses from the floor if it's a slab on grade wall, slab on grade floor. So we'll just estimate this one at 4-inch block wall, brick facing. You can have the option of having an insulated or uninsulated perimeter. And this is not wall insulation, this is perimeter insulation. So this would be at the footing of the wall or the just below the slab floor. And then your exposed perimeter. So let's just say 10 feet for this. You can add a floor covering as well. So we'll just show what that looks like. This would be things like carpet, tile, hardwood. So it just adds a little extra R value, which is sometimes not shown in architectural floor types. So if you had that in addition, that's where you can add it. You will have this loads preview button here, and this is quite valuable to see how the loads are actually being calculated and what the impact of your floor is. This is going to be based on estimates for your indoor temperature. Of course, if you do have a different indoor temperature, it will be different than this, but it just has to make an estimate to perform the calculations. So, for example, if we change this to a 100-foot perimeter, you can see that the load has now changed. And as you can play around with that to see the effect, you'll notice that cooling is 0 here, and that is because there is no cooling load associated with a slab on grade floor. You can go basement. This one has a little bit more complicated inputs, so we'll go over this as well. I won't go over the other ones because this is just a high-level overview, but basement is worth going through. So you'll have these options here. So for depth, let's say 6 feet below ground. This is how far below that the grade level the floor actually extends. Um, Again, we can refer to our quick help here. Slab below grade. It gives some descriptions of what these inputs mean, and this one is a fairly extensive one, as you can see. The R value of floor insulation, so this would be in addition to a concrete floor, assuming it's a poured concrete floor. If there's any other additional insulation, this is what would be entered here. The wall insulation, again, this is in addition to a poured concrete wall, so we'll just give it 5 for now. The shortest width of the basement, it's a kind of a strange input, and sometimes you might not even have a rectangular basement, but this is an input used to estimate how the heat transfer really works and the nature of it. It's to do with the shape of the floor, and this can be the shape of the floor can be inferred from the area and the shortest width. So let's say this was 20 for this example. Maybe that's not realistic. We'll go 10. And you have your below grade wall area. So that would be, in this case, 6 feet below grade. Whatever the perimeter is, it would be 6 feet multiplied by the perimeter. I'll just say 120 feet for this example here. Again, it's not realistic based on these numbers, but that's okay. The amplitude of the ground surface temperature variation is a somewhat more complicated input, and it actually comes from this diagram here. This little dot shows Atlanta, Georgia as an example, which is the same example we've chosen for this project. You can see that it's between the 18 and the 22 degree Fahrenheit lines. This value will be estimated for every location in North America. So for this example, it's at 19 degrees Fahrenheit. We can choose an automatic value here. So we can choose a manual value if we want to override this. Let's say we wanted a higher amplitude at 25. This would make it colder in the winter and hotter in the summer. But I will just go with the automatic value. And the average ground temperature value, and this is pulled from the weather data as well. So both these values are pulled from weather data. You can override this if you like. You can also override both of these values from your location data, but I will just leave them both as automatic. And again, you can add the floor covering, so we'll just go with the carpet. And you can see your load preview here based on the inputs you've given. And you can see how this changes as the inputs change. So for example, if you wanted to change your wall area and maybe change your depth, you can see how that will affect that heating load. And again, there's no cooling load associated with a basement, and that's because the ground is typically cold and you will not get much heat transfer. It's really only adding to the heating load. You can collapse that load preview at any time. And like I said, you can add as many floors as you like. So for this example, to make sensible calculations, we'll actually delete this floor and proceed without a floor. In reality, what we'll be doing, what this example would have is a floor above a conditioned space, which actually, as you can see, provides no heat transfer whatsoever. So that would, adding a floor above conditioned space is the same as not adding a floor. The next and last piece of the envelope details are the partitions. A partition is a wall that separates your space from an unconditioned or a partially conditioned space. This means that the wall is not directly separating your space from the outside, from the elements and from solar gains and from the outdoor air. It's also not separating your space from a conditioned space. If it's separating it from a fully conditioned space that's approximately at the same temperature, you'll have no heat transfer between your space and what's on the other side of the wall, so you would not add that as a wall. But if the thing on the other side of that wall is something that you will expect heat transfer from, then you'd want to add a partition. So good examples of this are like a parking garage or a warehouse maybe that's only heated to a colder temperature. Maybe it's only heated to 55 degrees in the winter and then is not cooled at all during the summer. then that's when you would add a partition. So we'll go through the exercise of adding one. So the first thing you'll do is add a wall type, and this comes from your wall list again. So if I click this, I will actually add a new wall type. We will call this partition 1. The type, we will just say it's a concrete block wall for now. Since it's not an exterior wall, maybe it's only an R value of 15. And the wall weight actually does not make a difference for the partition calculations, so it really doesn't matter. So maybe we'll just go with 30. The solar absorbance also will not matter for a partition because it's assumed that there will be no solar loads to it. So we will go with 0.5 as just a kind of a random estimate, and we can select that. You'll now enter the total area of the wall that separates your space from the buffer space. So let's say it's 100 square feet, and you have to select the buffer space that it is being separated from. So the buffer space is built in the buffer spaces tab here. You can add multiple buffer spaces, but each partition separating a space, a conditioned space from an unconditioned space is between your space and one buffer space. So a buffer space, creating the buffer space is like creating the parking garage or the warehouse or whatever unconditioned or partially conditioned space that your area is separated from. The reason it's created separately here is because you may have multiple spaces that you want to create that will all have a separation between them and the particular buffer space. So we will call this one parking garage in this example. You can then enter your temperatures manually, or you can enter them you enter details by building your buffer space. Manual entry is simpler but may not be as accurate. So if we enter, we may say it's up to 90 degrees in the summer, and in the winter it'll only get to 55. Or we can say we don't know what the temperature will be, but we will build it. So what you would do is build by adding walls. So for example, let's say it's a brick wall on one side, and there are maybe 3 walls to this space. So we'll just add another brick wall, and we will add a partition wall. Each one has an R value, and you can also add just a manual wall. Maybe you don't want to create a wall type for this purpose, you just want to add another basic wall with a manual R value. You can just enter it like that. You provide an area for each wall. So you're defining the enclosure of the buffer space. You give every area or every wall an area, and you select what it is adjacent to. So is it adjacent to the outdoors, indoor, or other? So let's say the brick walls are both, or let's say one brick wall is separating the buffer space from the outdoors, one is separating it from the indoors, from an indoor temperature. The partition separates the buffer space from an indoor temperature, and the manual one separates it from something else. And what it separates it from is, let's say 80 degrees in the summer and 60 degrees in the winter. The advantage of building a buffer space like this is that it actually calculates the temperature dynamically depending on where you are in your simulation. So during the winter, the outdoor temperature will be very different than the summer outdoor temperature. So the output buffer space temperature will change with the different time and month of your simulation. Let's estimate a little bit of infiltration, and we'll say that there's no heat gain. And you can see we have output estimates for our buffer space temperatures based on our peak temperature loads, but as the simulation goes on, these temperatures will be varying as the outdoor temperatures change. So for this example, since these are all kind of made up inputs, we will just go with manual input temperatures, and we will assume these values here, and we'll go select, and we now have a partition between our office and the parking garage, and we will expect a little bit of heat transfer between the wall separating them. The final section of doing your space inputs is the internals section. So you can see this is separated into 5 categories. So we'll start with people. You can enter either directly the number of people you expect, or for larger areas where it's a little more unknown, you can enter by density. The density has a reference table just like some of the others. So, you can see, for example, hotels, dormitories, barracks, sleeping area, 20 people per 1,000 square feet, and so on. Office buildings, break rooms, 50 people. So you would find whatever one is most applicable, and you could enter that, and it would calculate the number of people based on the occupancy, or based on the floor area you gave in your general inputs. So you can see here, based on that, we would get 8 people. Now, realistically, for a 150 square foot office, 8 people is unrealistic, so I'm not going to enter that. I'm going to enter directly the number of people, which I expect just one person for this office. You can also select the activity level. So we'll say moderately active office work sounds about right here. That will adjust the sensible and latent load per person, as well as the radiant fraction. You can also change the schedule, and schedules, like some of the other items, are edited and created in your schedules tab on the left. You can also do it from within your space creation. So you can see here we've got 2 default schedules already created. This will always be the case for any project you create. There's an always on schedule if you want something to be just on throughout the day from start to finish. And there's also a work hours schedule. So if you're unsure what the work hours schedule was, you could just click edit, and you'd see that it's 9 a.m. until the end of 4 p.m. So this is the 9 a.m. to 10 a.m. bracket, and this is the 4 p.m. to 5 p.m. bracket. So this is saying basically 9 to 5 it's occupied, and other than that, throughout the other hours, it's not occupied. So I think what I'm going to do is actually increase this a little bit in a few areas. So you can either use the sliders to do that, or you can enter the values down here. So I'm going to increase these, and this is to account for the possibility of cleaning staff who might be going into and out of the office after hours. So we'll do that. Actually, we'll take that one. So we will adjust our schedule like that. The next section is lighting, but before we move on to lighting, I'll just show you, going back to the ventilation calculations, how the occupancy affects it. So if we open up our ventilation, you can see our total ventilation preview is 14 CFM now. And that's because it's taking 5 CFM from this one person. So if we increase that to, let's say, 10 people, you now see 59 CFM, and it gives you the breakdown of the calculations. So we'll change that back to 1. And actually, while we're here, if we look at the infiltration calculations, because we added a wall, we now have 100 CFM, or 100 square feet of exposed area from that one wall we had, and that results in 5 CFM of infiltration. So as you go and populate these inputs, you'll see that previous load calculation previews will become updated. So moving on to the lighting. The people and the lighting are the 2 most important internal loads typically. So for lighting, you give a power input, and it can be in various units. You can go just straight watts per square foot, or BTU per hour, and BTU per hour per square foot. So most common is the watts per square foot. And this also comes with a lighting power reference. So you can see for different types of spaces, there's a typical value to use. So if we go down here, we'll see office enclosed less than 250 square feet. A typical value is 0.74. So I will use that for this one. You can also get these values from an electrical consultant who's working on the project with you. They may have a more accurate value of what they plan to install. The radiant fraction and space fraction items are a little bit more complicated, and they come from the luminaire reference. So different types of lighting types will have different radiant fractions and space fractions. Of course, these are estimates. They will not be exactly correct, but a reasonable estimate will be better than just no estimate at all. So, for example, a recessed fluorescent luminaire with a lens, 67% radiant and 45% space fraction. So I'll enter 67% radiation here. The space fraction is a little bit more complicated, and of course that will be found in your quick help menu under lighting. The space fraction is to account for the fact that if your light is installed in a ceiling, in a ceiling that is dropped and there's a ceiling plenum above, some of the heat from the light will actually radiate upwards into your ceiling plenum and never really enter the space. Some people prefer to just account for the full lighting load in the space, and some prefer to add the normal amount to the plenum that would be expected. For this luminaire type, it was 45%. So I actually will add 45%, and that's because it's a recessed light fixture, so it is into the ceiling plenum and shining downwards, and a lot of the heat generated from that light will actually be given off in the plenum. That load will still be accounted for. 100% of the lighting power will be added to the system. It's just a matter of how much goes into the space versus into the return side on the air handling coil. So we then have an option of changing the schedule for the lights as well. So for this one, I will actually leave it as always on because a lot of the time lights will be on even at night, but I will duplicate it and make a copy of it and edit this, and I'll call it office lighting. For the office lighting, I will say it's a little bit less during the daytime. Maybe the lights have been dimmed during the daytime because it's already light outside. They're getting some daylight, and I don't want to account for the full lighting load during the day. And then at night, when the cleaning staff come in, it's on, and it remains on throughout the night, as many offices do. I will select that, and you can see that there is a little bit of info here about that radiant fraction and sensible and the space fraction, and we have our load preview right here as well as these values. So if we changed our 0.74 to, let's say, 0.8, you'd see our load preview would change, and that is based on the floor area given in your general inputs. So the next one would be motors. Motors is a fairly uncommon input to use, but in case you do have a situation where you've got a particular motor in the space, such as a fan or a pump that's giving off heat, you can add the motor by horsepower and by efficiency and quantity. You also have a motor reference table, just like the others, to help with the efficiency values. So I won't go into too much detail here because this is a pretty uncommon input, but that is an option. You then have the option of adding appliances. So you can enter an appliance manually by power. This requires sensible and latent power as well as a radiant fraction, and a schedule and a quantity. Schedule very similar to the others, of course. Radiant power is something, radiant fraction is something that's very hard to know beforehand and based on different types of appliances. So we do have lists to select from. So if you select from a list, you can select different categories of appliances. So for example, if we went laboratory equipment, a small centrifuge, This would give us automatically populated sensible load, latent load, and a radiant fraction for this appliance. And a preview here of what's happening. There's also the option of selecting for office space, and this is more for open office area with many desks. So you can select an intensity, types of workstations that are expected, so laptop, desktop, and so on. And there's some information on that below here for office load factors and so on. For this one, I will select from the list, and I will select from office desktop computers. We'll assume this office has a computer. We'll go 16 gigabyte RAM. It's a pretty common value. And we'll say it's just one. And for the schedule, I will create a new schedule, but I will duplicate the work hours schedule because it's going to be pretty similar. And I will call this computer, so I know what it's applied to. We'll assume it's about 20% most of the time at night, because it will be giving off a little bit of heat. It will still be on, and then it will be fully used during the daytime, and then back down to 20%. That's just my estimate of the behavior of the heat generation from the computer. And you can see here it auto-populates with its estimate of the radiant fraction versus convective fraction, so it's 10% radiant here. And you can add as many appliances as you like, but we'll leave it as one for now. And then there's the last one, miscellaneous loads. So this would be for anything that you don't want to go through the trouble of adding an appliance or a motor and it's not lighting, something that you know the sensible and latent loads that are being given off, and you'd have to manually estimate a radiant fraction for any miscellaneous load as well, and select a schedule. This can also be done as straight BTU per hour or per square foot, or watt per square foot as well. Once we've created a space, we can go back to our list and check our entire list of spaces. So we've currently got just the one. I'll show you an example of just duplicating a space. So you hit duplicate and go to edit the space. You can change the name. So I will call this one Office 2. And this one will be a little bit different because instead of having an east wall, let's say this one has a south wall with everything else staying the exact same. So using the duplicate space option is quite useful. Once we've created our spaces, we can then go to back to our guide and mark done our step 2. The next step would be to create our system. Now, ideally, you should not be creating your systems until you've completed all of the spaces that you think you'll need for running your system calculations. But I'll show you the steps of going through how to create your system, and you'll see why it's necessary to have all your spaces. But for now, let's create a system, and we'll call it Air Handler 1. And what we need to do is define our zones first. So you can see it comes default with one zone, because you cannot have less than one zone. We'll call this one, let's say, east side. So this will be on the east side of our building. And it has currently Office 1 in here, but I could change that to Office 2 if I wanted. Office 1 had the east exposure, so I'll leave it as that. And we'll say it had a quantity of 2, so it had 2 identical offices in this. So if you have multiple of the same office, you don't really need to create the office more than one time. You can just add multiple instances of it into your system. You can then define your indoor temperatures that you anticipate for this zone and what it will be controlled to. So the default is 70 Fahrenheit indoor winter temperature and 75 for summer and 50% humidity for summer. I will just leave those defaults as they are. And I'll just add one more zone. You can add as many zones as you like, and for large systems you'll likely have quite a few. For this one, I will just change it to Office 2. And actually, I will add one extra space, we'll say one instance of Office 2 and one instance of Office 1 in this zone. The temperature and humidity inputs, again, I will just leave as they are, but they are adjustable. So once you've finished your zone inputs, then you can move on to the general system inputs. First one is the estimated total system occupancy. This is to avoid double counting occupants. So for example, if you have a bunch of offices with occupants in them and you have a break room and a boardroom or something, you would expect that the people who occupied the offices would also be the ones occupying the break room and the boardroom just by moving around at different points in the day. This is only affecting the ventilation calculations. So if you're going to be overriding the ventilation values in this ventilation section here, which we'll get to in a second, then this doesn't really matter. But if you're not overriding that, then it's important to give an accurate total occupancy value to make sure that the calculations, when they're calculated by the software, are going to be accurate. So for this example, we'll just go with an estimated occupancy of 5 for the total system. You then select your system type, so you can select a constant air volume or variable air volume system. So for this small system, we'll do a CAV. The next input is your separate airflow for heating and cooling. And this is a very important input because if you select no, that would mean that you're having the same airflow for heating and cooling. And what that means is if your cooling outputs give you an airflow of, let's say, 2000 CFM and your heating gives you 1500 CFM, it means it will take the higher value and assume that that is your constant airflow volume all year long. So if your higher value was 2000 CFM, it will apply 2000 CFM all year long, and that means during heating season, it will use that full 2000 and determine how much heat you need to get that full 2000 CFM up to the heating supply temperature, which might not be as accurate and might give you a higher heating value than what you would actually technically need, because maybe you could achieve the same heating or achieve your heating load with a lower supply temperature. So if you don't want your heating and cooling loads to affect each other, then you should select yes. However, if you do have a system where you know that it's going to be a constant airflow the whole time and you want to make sure you're achieving the proper supply temperatures for heating and cooling, then it may be more accurate to select no for that value. For example, a constant volume furnace that will be delivering the same airflow all year long and cannot change the fan speed, it might be more accurate to select no. But for this example, we'll go with yes. You then have your supply air temperatures for both heating and cooling. So these are the default values that are provided, and I think we'll just stick with those for this example. The next one is zone terminal reheat. For this one, we'll use no, but if you had a situation where you had let's say a VAV system with terminal units and you were adding electric reheat coils, this would be used for that kind of a situation. And then the zone airflow calculation method, you can select sum of peaks or total peak. The sum of peaks means that it takes the peak airflow at each space by calculating the airflow at different times of the day and of the year. It'll take the maximum for each space and add that maximum together, regardless of whether or not those maximum airflow values are happening at different times. So for example, if in Office 1 you had a peak time at July 3 p.m. and for Office 2 it was July 6 p.m., it would just take those two values and add them together even though they're happening at different times. If you did a total peak, it looks at the zone as one big chunk and says when is the maximum airflow for this zone as a whole happening, and it takes that as a singular value. So for this example, we will go with the total peak option. For the ventilation calculations, even though you've entered ventilation values for your spaces, this is what will round it all up into a system ventilation intake value. So if you look at the ventilation section here, it will describe some of the calculations going on and why this is important. Ultimately, it's for this VOT value, which is dependent on the space ventilation values, but it has to be all put together in the calculations, partially based on that total system occupancy, partially dependent on some other factors. If you decide to do the calculations yourself, which some people prefer to do so they have more control over it, you can just go with a yes on this override system ventilation intake, and you can provide it a minimum value and a maximum value. The reason that there's two different ones here is because if you're using demand control ventilation, then it will modulate between the minimum and the maximum depending on system occupancy, and that will come from the occupancy schedules that you provided in your system, or sorry, in your space's inputs. So if you don't have a demand controlled ventilation, then the minimum doesn't matter. You could just do 0, and the maximum you could make whatever would be your realistic value. Let's say 300. For this example, I will go with no. I will have the ventilation calculations automatically done. And for demand control ventilation, I would just do no in this case as well. For a CAV system, that's more common. For heat recovery, I think I will do an HRV. So you can go with none, HRV, or ERV. The difference between HRV and ERV being that for an ERV, you give a sensible efficiency and a total efficiency for both summer and winter. For an HRV, you just give the efficiency values. These are sometimes called effectiveness on a cut sheet for an HRV or an ERV. So if you have those values, that's what you would put here. For the exhaust flow through your HRV, you have a few options. So the ventilation flow through the HRV will be equal to your total ventilation. Exhaust flow, you can have it match the supply flow. If you don't know what your system ventilation is, this is a good option. You can have it as a specified portion of your supply flow. So for example, if you're trying to positively pressurize the space and you're only taking, let's say, 90% of exhaust compared to ventilation, you want a 10% reduction in your ventilation to provide a little bit of positive pressurization, then you would put, for example, 90% here. If you know the exact CFM value of your exhaust flow, you could enter that as well. This is more common if you're entering the ventilation manually. So let's say if you had 300 and you know that you're negatively pressurizing the space by 50 CFM, then you could do 350 CFM of exhaust air. For this example, I will just match the ventilation, and I will give it a value of 50% for summer and 60% for winter. There's also an advanced drop-down. So one option is to change the ventilation modes or ventilation values for heating and cooling modes. This is recommended if you are doing your separate airflow for both heating and cooling. If you're keeping the airflow the same, or you know that your flow through your HRV or through your whatever your ventilation unit is not going to change and it's just going to be constant speed, then it may be better to just use no for this value. If you say yes and you override your system ventilation intake, it will be the same value anyways. It will not differentiate between heating and cooling. But if the values are calculated automatically, then it will take into account the effectiveness values that were given in your space ventilation inputs, your EV. So if we return there for a second to your ventilation, you had an EV or EZ value for cooling and an EZ value for heating. That would then be taken into account if the change ventilation for heating and cooling modes input was set to yes. So for this example, I will stick with yes. And the other advanced option is to add an economizer. Now for peak load calculations, an economizer usually will not make a difference because it's usually happening, your peak calculations are often happening when the outdoor temperature is at a very extreme value and you are not getting the advantage of using an economizer. But there are times when it might affect your peak cooling loads, and adding an economizer, if it will be used, is a good option to include. So for this example, I actually will select yes. And then we can move to the air handler fans. So you have the option of adding a supply fan, and a return fan. You do not have to add them. You can just simply select no for both of them. If you have one fan in your unit, for example, packaged rooftop unit would likely only have one fan, but if it's a larger air handling unit with both supply and return fans, then you can add both. You can select if the motor is in the airstream or not, and this will make a difference in terms of how much heat from that fan motor enters the airstream and will have to be accounted for in your cooling loads. The external static pressure would have to be estimated. Now, if you have no idea what it is at the moment, you can refer to this guide for different system sizes. You can have different reference ESP values, external static pressure, as well as fan and motor efficiency values. So in this example, I will say it's a pretty small system, and we will go with 0.5 for static pressure. This is also heavily dependent on the farthest length of duct run. So for buildings where your air handling unit is very centralized and is not sending air very far away, then it will be a lower value. But if you are sending air very, very far away, this value will need to be increased. For motor and fan efficiency, for a small system, I will just keep the 75% for each because those are the recommended values. And I will finish the air handlers. With your system inputs, you can go back to your list of systems. So you can see we've only created one so far. So I'll show you an example of creating another one by duplicating this first one we created. So if we go into this new one that's a duplicate, it's exactly the same, and I will just change the name, call it Air Handler 2. This can be a great tool to use for comparing slight changes in your systems. So for example, if we wanted to see the impact of our HRV, we could just select none for Air Handler 2, and then Air Handler 1 is the exact same as Air Handler 2, but with an HRV, and see how that affects our total loads. So going back to our guide, we'll see that systems is done, and our next step is just to run the calculations. So if we go to our results tab here, we'll see both of the systems we've created so far. If we click results, we get this button here to run our calculations. So if we click that, we'll have our option of first selecting which design temperatures to use. So for heating temperatures, these are the 99.6 and 99% annual temperatures. So we'll go with 99.6 for this example. For cooling, these are the monthly temperatures, not the annual temperatures. So we will go with 2% for this example, but you've got a few different options here. And then hit calculate. And as the results are calculating, you can see it shows you your progress, including the so first of all, the system loads, and then first the space loads and then the system loads. And once this is done, we will see all of our results displayed. So you can see it tells us our system type, our peak heating load, our peak cooling load, our heating airflow, and our cooling airflow. And it will also give us a number of charts, bar graphs, heat map, further detailed results. You can see, for example, if there are any issues. So this issue here, diversity of 1.25, that's because in the general inputs of the system, I put an occupancy of 5 when the sum of the occupancies from all of our spaces in the system was 4. So that's where that issue arose, which is a very unusual thing, but you can see that it still proceeded with the calculations, just telling us that something unusual has happened. We can see our zone load breakdowns, further details in our space loads, and you can expand any of these and see further details and even see the space load breakdown by pieces, so our windows, infiltration, walls, partitions from heating, and also the cooling and the cooling breakdowns for every space. You can see it goes quite in depth, and this is available for every space, and it even gives us our temperature profiles, solar irradiance on different wall angles, and so on. Once you've gathered your load calculation results, the last step would be to export your results so that you can save them to your desktop. So I will just scroll back to the top here and you'll see an export button. You have the option to export to an Excel format or to PDF. In both options, you'll have a series of things that you can include or exclude from your downloaded results. That's just for if you want to make the results or the file a little bit smaller. So for this example, I'll just do a PDF export. And once it's loaded, we can open it up and it can be saved to your desktop to permanently save the results or to share with other people. So you can see here we've got our results and it just shows it in a nice PDF format. Same exact information that was on the website, just a little bit of a different order, but nicely summarized. So that is a basic summary of how to make a project, build your spaces and systems, and run your calculations on HeatWise. For more in-depth information on all the specific aspects, we'll have separate unique videos for each topic. And of course, when you do your load calculations, you can keep redoing calculations, testing out different scenarios. You can even recalculate, change your design temperatures, and so on as much as you like, and keep downloading, comparing results.